The other day I googled a simple question. Can a redox reaction have only one reagent? The answer that was generated by AI surprised me. It said no. A redox reaction cannot have only one reagent because it fundamentally involves the simultaneous transfer of electrons, meaning one species must be oxidized and another must be reduced. In this video, I would like to demonstrate to you that this answer is at best quite deceptive and at worst completely incorrect. Hello chemistry champions, this is Werner. Welcome back to the channel. YouTube has several excellent videos showing how to balance redox reactions. But in this video, I want to focus on a special case, on how to balance redox reactions where the equation has only one reagent, because this type of question can trip you up if you're not familiar with it. The thinking is then a bit like the AI-generated answer. There must be two reagents, because surely only one species cannot both be oxidized and reduced. But in fact it can. In redox chemistry, such a reaction has in fact a special name, called a disproportionation reaction. We look at three examples: a metal oxide, a non-metal oxide, and a form of elemental phosphor. All of them are the sole reagent. By the end of the video, you will be able to know all the steps involved in the half reaction method, in balancing redox reactions in both acidic and basic media, and more specifically, you will also have the tools necessary to deal with the somewhat unusual redox reactions, so you know what to do when you recognize them in future. With that said, let's have a look.
Right, let's get started with the first problem. Maybe not a bad idea to start by first naming the species that's involved. You have MnO4 2-, that is called manganate ion. You have MnO2, that is manganese dioxide. And you have MnO4-. This is permanganate. So permanganate, manganate. I also indicate here the different phases in which these chemical species are involved in. This is AQ, aqueous. It means it's in a watery solution. Manganese dioxide is a solid, S, and this one is also aqueous. So I won't use these phases again, writing them down going forward, just so you know in which phases these different species find themselves. Now it says here in step 1, determine the oxidation numbers. So that's always the first step that you want to follow. So we know that oxygen is always 2-, and you have 4 of them, and the total charge of the species must be 2-. So that means the manganese must be 6+. Here you have manganese dioxide, oxygen 2 minus 2, or 2 times -2 is -4. To balance that, to give a neutral species, means that the manganese must be 4+. And the permanganate, 4 times -2 is -8, and the total charge must be a minus of all the elements involved. So that means the manganese must be 7+, which is a very high oxidation state for a metal to be. Right, so that is then determining the oxidation numbers. The next step is to figure out what is the oxidizing and reducing agents. And you do that by looking at the oxidation numbers and how it has changed. We see here that the manganese have gone from 6+ to 4+ in this case. So that is referred to as a reduction because the oxidation number has decreased. And in the other case, the oxidation number went from 6+ to 7+. And that is an oxidation because the oxidation number has increased. So now we know that the manganate has oxidized with respect to the permanganate, and it has reduced with respect to manganese dioxide. Moving on to the next step, write the half reactions. So you have manganate, giving the permanganate in the oxidation step, and you have the same reactant, manganate, giving the manganese dioxide in the reducing step. Those are the half reactions. Step 4, balance atoms other than oxygen and hydrogen. Now there's only one atom other than oxygen and hydrogen, and that is manganese. You see you have one here, one here, one here, one here. So there's nothing to balance with respect to that. Step 5, add water to balance the oxygen, add H plus to balance the hydrogen. In the first half reaction, you have 4 oxygens and 4 oxygens, so there's nothing to balance. In the second half reaction, you have 4 oxygens, and on this side only 2 oxygens. So to balance the oxygens, you add water, and since you have 2 oxygens here, you need 2 water. Balance the H plus, balance with H plus all the hydrogens. On this side you have 2 times 2 is 4 hydrogens, so you need 400 H pluses on this side. And now everything is balanced with regards to all the atoms, all the oxygens and all the hydrogens in the appropriate way. Step 6. Let all the electrons balance the charges. So the charges in the first half reaction, on this side you have 2 minus, and on this side you only have 1 minus. And the electrons are always added on the more positive side. So here you need 1 electron. In the second reaction, you have 4 pluses and a 2 minus. That gives a net of 2 plus. On this side you have neutral molecule, neutral molecule. So there's no charges to consider. So the only charges to consider is on this side we have a net of 2 plus, and that must be balanced with 2 electrons. One thing to look at when you get to this step in solving the problem is that you must have electrons on the right side and you must have electrons on the left side. If you have electrons on either side, then it means somewhere you've made a mistake, because then it means both half reactions are either oxidizing or reducing. So just check that and then make sure that you get it right up to this step. Step number 7. Let the number of electrons become equal by multiplying the half reactions. So what that simply means is that you need to balance the electrons. Now here you have 2 electrons, here you have only 1. That means this reaction totally in its totality must be multiplied by 2. So 2, 2, 2. Now what has happened is all the charges have been balanced, and you've also balanced the appropriate atoms in the reaction. This is a step that people sometimes do incorrectly by simply multiplying the electrons, but you must remember that all the species involved must be multiplied with the appropriate number of coefficients. Right, then for the last step, as it pertains to balancing the reaction in an acidic media, is that you add the half reactions and you cancel what I call the spectator species. That is simply species that can be cancelled on both sides. So if you add them, you have 2 electrons plus 4H plus, you have 2 manganetes here and 1 here. So together you have 3. And on the right hand side you have 2 permanganates plus manganese dioxide plus 2 waters plus 2 electrons. Now the only things you can cancel at this stage are the 2 electrons on both sides. And what is left is a balanced redox reaction. If the question were to ask balance it in an acidic media, the H plus here gives a big clue that it's in acidic media. Now if the question asks that you must balance it in a base or basic solution, then there's additional steps to be done, and they are as follows. For a base, for each H plus add a hydroxide on both sides. You have H plus, 4 H pluses on this side. So you need to add 4 OH minuses on that side, and you need to add 4 OH minuses on the right side. And then notice that this together becomes 4 H2Os combine H plus and OH to make water. That's what we've done here. And subtract water on both sides if needed. In this case you do have waters on both sides, so you can cancel that and you can cancel this. 4 minus 2 equals 2H2O. So with all that you can write the final equation for a base, which is 2H2O plus 3 manganese manganate. That provides 2 manganese plus manganese dioxide plus 4 OH minuses. And there you have it, the final reaction balanced in a basic media. So moving on to the next problem. Here we have the redox reaction. And I think it's a good idea again to start by naming the different chemical species involved. ClO minus, that is hypochlorite. Cl minus, that's obviously chloride. ClO3 minus, that is chlorate ion. Again, all of them are in the aqueous phase, designated with the AQ. And so the first step is to determine the oxidation numbers in each case. ClO minus, the oxygen is 2 minus, the total charge is 1 minus, so that means the chlorine has a +1 oxidation number. In this case you have an monoanion, and that will have the same charge as the ionic species, so that will be -1. And here you have, for the chlorate, ClO3 minus. The oxygens are 2 minus each, times 3 is minus 6, but the total charge is minus 1. So that means that the chlorine in this case has a charge of plus 5. So there we have determined the oxidation numbers, and we can clearly see that it must be some kind of redox reaction because all the oxidation numbers are different. In the next step, we try to figure out what is the oxidizing and what is the reducing reagents or agents. And we can tell that for the hypochlorite species here, the oxidation number goes from plus 1 to minus 1 in this case. So that is a reduction because the oxidation number decrease. And in this case, the oxidation number increase. So that is the oxidation. So that is the respective way in which one can have the oxidation numbers. Just a reminder again that the oxidizing agent is the one that gets reduced in the process, and vice versa for the reducing agent. Step 3, write the half reactions. So you have ClO minus, that provides chloride, and ClO minus to become the chlorate ion. Those are the two half reactions in step 3. In step 4, balance the atoms other than oxygen and hydrogen. The only other atom involved here is the chlorine atom, and we can see that in each case it's a 1, 1, 1, 1 situation for the coefficients, and also it has no subscripts, so that step is done. Step 5, add water to balance the oxygen, add H plus to balance the hydrogen. We see here 1 oxygen, and so we need to balance that with 1 water. And we see here 1 oxygen again, and we see here 3 oxygens. That means on this side we require 2 H2Os. And then we need to balance the H pluses with a H. On this side we have 2 hydrogens, so it means here we need 2 H pluses. And on this side we have 4 hydrogens, 2 times 2, 4 hydrogens, so it means on this side we require 4 H pluses. And now we've balanced all the atoms, all the non-hydrogen and oxygen atoms, and all the hydrogen and all the oxygen atoms. So then we can move on to the next step. Let the electrons balance the charges. So we need to figure out what are the charges. Here you have 2 H pluses. You have a 1 minus and a 1 minus, so these 2 minuses cancel each other. And you're left with 2 H pluses or 2 pluses. And we always add the electrons at the side that's the most positive. So this is going to require 2 electrons on that side to balance all the charge. On this side, you have a 1 minus, a 1 minus. Again, this balances each other out. And here you have 4 pluses. So you're going to require 4 electrons on this side. And again, as with the previous example, make sure that your electrons are on opposite sides of the equation so that you have an oxidation and a reduction as required. In the next step, let the number of electrons become equal by multiplying the half reactions. So here you have 4 electrons, here you have 2 electrons. So for this reaction to equal these electrons, you need to multiply all these species by 2. Right? So I will write the new reaction on top here, but basically what you need to do, all of this must be multiplied by 2. So here you have 4 electrons plus 4H plus 2 ClO minus, and that gives 2 Cl minus plus 2 H2O. And now you've balanced the electrons by multiplying the relevant half reaction appropriately. And then you can add the half reactions, and you can cancel all the different species that are redundant, that can cancel each other. So we're now dealing with this top reaction and the bottom reaction. So let's first add up everything, and then we can see what's left after we've cancelled it. You have 4 electrons plus 4H plus 2 ClO minus, and and here you have 2 H2O, ClO minus plus ClO minus, that's basically 3 of them, so I'll just change that coefficient. That provides 2 chlorides plus 2 chlorides, that's it, plus 2 H2O plus 4 H pluses plus ClO minus 3 plus 4 electrons. Then if we cancel out what's not needed, you have 4 electrons there, 4 electrons here, you have 4 H pluses there, you have 4 H pluses here, and you have 2 H2Os there, you have 2 H2Os there, and all you are left with is 3 ClO minus gives 2 Cl minus plus ClO minus 3. Very interesting, because we've supposedly balanced it in a acidic media, but notice there's no H pluses left in the equation. Now, what I would like you to do for yourself is to take the steps that we've done in the first example that I reiterate here. For each H plus, add a hydroxide, etc. Combine the H pluses and the OH to make water, and subtract water on both sides if needed. And what you will discover is that this reaction remains the same after you've done all these steps. So the reaction is exactly the same whether you work in an acidic or basic medium. So that's quite interesting. Right, let's look at the final problem in this video, which I think the final result will also prove to be quite interesting if you haven't encountered this type of situation before. Let's first look at the chemicals involved. You have P4, which is an allotrope of phosphorus in the solid state, is also known as white phosphorus. You have HPO3 2-, that is hydrogen phosphite. Notice it's got 3 oxygens, so it's phosphite, not a phosphate. in aqueous solution. And you have phosphorus trihydride in the gas form. This is also commonly known as phosphine. And I guess the IUPAC name is phosphane. So it gets a bit complicated. If we look at determining the oxidation numbers, we know that an element in its native form has an oxidation number of 0. So phosphorus there would be 0. In this case, the phosphorus atom, you have 3 oxygens. Each oxygen is 2 minus. And then you have a H plus. And the total charge must equal 2 minus. So that means the phosphorus must be 3 plus. And then finally here you have the phosphine. Now one might be tempted to think that could be 3 plus as well, because one name here of this species is phosphorus hydride, which makes it a bit confusing because we know that a hydride is a H minus. That would make you think that this phosphorus is 3 plus. But of course then you have 2 3 pluses, so there's no redox reaction. And so in situations like this, what happens is the hydrogen is always assigned as a 1 plus. And so this phosphorus is 3 minus, despite its name that can sometimes make it a bit confusing. So that is determining the oxidation numbers. So from there you can clearly see that there is a redox reaction going on. The next thing is to figure out what is the oxidizing and reducing agents. Now the oxidation number increases from 0 to 3 plus here, and that means this step is the oxidation, and the oxidation number decreases from 0 to 3 minus in this step, which tells you that this is the reduction because there's a decrease in oxidation number. The next step is to write the half reactions. So you simply have P4, and that gives HPO3 2 minus, and you have P4 gives PH3. And those are the two half reactions involved. I'm not including the phases in this case. Just so you know they are there. Balance the atoms other than oxygen and hydrogen. So in this case it gets a bit more interesting compared to the previous two examples where there was nothing to do in this step. Here you see now you have a P4, and here you only have one P. So that means this must get a coefficient of 4. Here you have again P4. Here you only have one P. That means you need a coefficient of 4 over there as well. And that is all the atoms other than hydrogen or oxygen. In the next step, you add water to balance the oxygen, and you add H plus to balance the hydrogen. So if we look at the first reaction, you have 4 times 3 is 12 oxygens. So you're going to need 12 waters on this side. Now you have 12 oxygens there, 12 oxygens here. For this one you have no oxygens, so there's nothing to be done. For the first step, you have a number of H pluses. So here you have 24 H pluses, and here you have only 4. So you need another 20 on this side. On this side, you have 3 times 4 is 12 hydrogens. So you're going to need 12 H pluses on this side. And now you've balanced for all the oxygens by adding water, and you've balanced all the hydrogens by adding H pluses. In the next step, you need to let the electrons balance the charges. In the first reaction, both these chemical species are neutral, so there's nothing to be done. Here you have a species that's 2 minus, and you have 4 of them, so that means it's 4 times minus 2 is 8 minus. And here you have a 20 plus. So the balance would be to add 12 electrons on that side, because here you have 20 plus. So that gives 12 electrons. And then if one looks at this side, you have 12 H pluses here, neutral, neutral. So you're going to need 12 electrons to balance these 12 H pluses. And they will go here. 12 electrons, like that. And that is then all the electron charges balanced. Let the number of electrons become equal by multiplying the half reactions. In this case, you have 12 electrons and 12 electrons, so there's nothing, so they simply balance out, and there's nothing further to multiply because the electron count is the same. The next step is to add the half reactions and cancel all the species that can be cancelled out on both sides of the equation. So you have 12H2O plus 2P4s plus 12H pluses, and that provides 4HPO3, 2 minuses, 20H plus, 4PH3. Right? Then, if one were to balance out everything, you can say that there's 12 of those, there's 20 of those, so that leaves 8 H pluses. And typically one would think this is the end of the story, but notice that this phosphite is basically a conjugate base of hydrogen phosphate. And so just like when you have a situation where H plus and OH minus reacts to give water, you have a similar kind of situation here, where these two will react if they're in solution. And so you have the 2 minuses, that is basically the phosphite that has lost 2 hydrogens, and here you have the hydrogens that it can now pick up. So the net result is that you can have 4H3PO3s, so that all of this H pluses are neutralized by this conjugate base, and plus 4PH3 on that side. And then on this side, you simply have the 2P4 and the 12 H2Os that's left. That then balances that part of the equation. And then if you want, you can divide throughout by 2. So that gives 6 plus P4 plus 2 H3PO3 plus 2 pH3. And that would be my final answer for the balance in an acidic medium. I can make one final comment, and that is that you can also do this in a slightly different way by multiplying P4 by 1/4, and you will find that if you add up all the electrons and you balance the half reactions, you'll get to the same reaction here. So when you leave it at P4, it just generates quite a lot of 12 waters and so on. If you have just 1/4 of it, then you see you'll only have 3 waters, but the end result is exactly the same.
And there you have it. 3 examples of balancing redox reactions that have only one reagent. I hope you found it of value. Let me know in the comments if you think of other reagents that can behave similarly. I think there are many. Please also consider to subscribe to the channel for similar content. Stay curious, thanks for watching, and check out my other videos on the channel where we solve interesting chemistry problems. Have a great day, and I hope to see you in the next video.